Hi students, now in this lecture we will discuss about the measurement of the electrode potentials. How do you measure the electrode potentials? If you take any electrode, you want to measure this electrode potential. For that purpose we take a reference electrode, right? So for the measurement of the different electrode potentials, we take a reference electrode. So reference electrode normally is the standard hydrogen electrode. Okay, so hydrogen electrode is taken as a reference electrode to measure the electrode potential of any other electrode. Suppose you want to measure the electrode potential of this electrode. Suppose we have a particular metal in a solution containing the metal ions. Now you want to measure this electrode potential. What I do, I'll connect this particular electrode with the reference, and the reference is the hydrogen electrode. So hydrogen electrode is taken as the reference electrode. Okay, and hydrogen electrode is made by passing the hydrogen gas at 1 atmospheric pressure through a solution which contains H plus ions. Like suppose we have a 1 molar HCl solution, right? If I take a 1 molar HCl solution and then pass the hydrogen gas through it at 1 atmospheric pressures, and to make the electrical connectivity we use normally the platinum electrodes. Okay, the platinum electrodes, which the platinum is inert, it does not react with the HCl. Okay, so this is made, used to make the electrical connectivity, and then we connect the different electrodes with the reference electrode, right? With the reference electrode, whatever is the electrode, suppose it may be the zinc, copper, iron, mercury, right? Whatever it is, right? So whatever the electrode potential we have, so the different electrodes we can take and connect them one by one with the reference electrode. Now by this way, once you connect it with the reference electrode, you get a galvanic cell. Here in this electrochemical cell, the hydrogen, the reference electrode, may either act as anode or it may act as a cathode. That means either the electrons will flow from the anode to the from the reference to this particular electrode, or the electrons will flow from this particular electrode to the hydrogen electrode, to the reference electrode. So that means the reference electrode may act as anode or it may act as a cathode. When it acts as anode, it will lose electrons, right? Or when it acts as a cathode, it will gain electrons, right? So it will form the hydrogen gas. The H plus ions, they will accept electrons and form the hydrogen gas. Or if it acts as anode, then the same hydrogen gas will dissociate into H plus ions and electrons, and then the electrons will flow through the wire to the other electrode. And this way we will be able to find the electrode potential of the different electrodes. Let's take an example here. Let's take one example to understand how we actually measure the electrode potentials. Suppose I have a zinc electrode, okay, in a solution containing the zinc ion, zinc sulfate solution. The zinc electrode, zinc rod dipped in a zinc sulfate solution at a 1 molar concentration and 25 degrees Celsius, right? So this is the standard condition. Now I want to measure the electrode potential of a zinc. So what I do, I'll connect it with the reference electrode. Okay, I'll connect it with the reference electrode. As soon as I connect to the this particular electrode with the reference, and I get one complete electrochemical cell, right? And we use the salt bridge also to actually complete the circuit. And what you get a complete electrochemical cell. As soon as you connect to the wire, the two electrodes through the wire, we find that electrons start flowing from the zinc to the hydrogen electrode. Okay, from zinc to the hydrogen electrode, which means that the zinc now acts as an anode, because since electrons are lost by the zinc and hydrogen gains them, and this acts as a cathode. Okay, so zinc loses electrons and the hydrogen gains. Electrode where oxidation occurs, that's called anode, and the electrode where reduction occurs, that's called as a cathode. So that means the cell reaction which actually occurs at the zinc is that the zinc dissociates into zinc ions and electrons. Okay, so therefore it acts as anode. The same electrons are accepted by the hydrogen ions. They gain hydrogen, they gain the electrons and form the hydrogen gas, and therefore it acts as a cathode now, right? when you connect to the two electrodes, you get a cell, right? You get an electrochemical cell, and let's suppose the EMF of the cell, the voltage of the cell here is 0.76 volts. Okay. Once you connect to the two electrodes, you get an electrochemical cell with a voltage of 0.76. What is this EMF? What is this electromotive force? EMF, or the electromotive force of a cell, is basically, it is the it is the sum of the two tendencies here. Okay, sum of the two electrode potentials. It is the sum of the basically it is equal to the oxidation potential of anode, right? It is actually equal to the oxidation potential of anode. Okay, so here anode is the zinc, so we can say it is the oxidation potential of anode, right? This is the oxidation potential of anode plus the reduction potential of a cathode. Reduction potential of cathode. In this particular example, reference electrode acts as a cathode here. Okay, and if the EMF of a cell is 0.76, you got the cell with a voltage of a 0.76. So oxidation potential of anode plus reduction potential of cathode. Now, since the reference is taken as a reference electrode here is a cathode, and we normally take the electrode potential of a reference electrode as 0. By convention, we take it as a 0. Okay, whether it acts as an anode or a cathode, right? Whether it acts as an anode or cathode, the electrode potential of this reference electrode is taken as a 0. By convention, it is 0. So if the reduction potential of a cathode here is 0, so what I got here? This is the oxidation potential of anode. So the EMF directly gives us the electrode potential, right? So what I got here, that oxidation potential of a anode of the zinc here is 0.76 volts. Correct? So I can change the oxidation potential of a zinc into this reduction potential simply by changing the sign. Okay, previously we have discussed that we can convert the oxidation potential into reduction potential and reduction potential into oxidation potential simply by changing the signs. So if I got the oxidation potential of a zinc is 0.76, I can find its reduction potential. I can say the reduction potential of the zinc then will be minus 0.76 volts. So which means that zinc has a high oxidation potential and a low reduction potential. Correct? Okay, so the zinc loses electrons once you connect it with the reference electrode. That's why it acts as an anode. So that means zinc has a high, relatively it has a higher tendency to lose the electrons, right, than the hydrogen. So hydrogen has a higher tendency to gain the electrons in comparison to the zinc. That's why the zinc will lose electron and hydrogen will gain, right? So that's why the zinc acts as an anode and hydrogen acts as a cathode. Okay, let's take one more example here. Suppose we have a copper rod. Okay, we got a copper rod in a copper sulfate solution. Okay, at a 1 molar concentration and 25 degrees Celsius under the standard conditions. Again, I want to measure the electrode potential of the copper. What I do, I'll make one complete electrochemical cell by connecting it with the reference electrode. As soon as I connect to the two electrodes here, what we find that electrons start flowing from the hydrogen from the reference electrode to the copper, which means that hydrogen in comparison to the copper has a higher tendency to lose electron, right? So copper has a high tendency to gain the electron. Okay, so therefore copper will take electrons away from the hydrogen, right? Hydrogen will not be able to take the electrons from the copper, right? Okay, because copper has high reduction potential. Copper has high tendency to gain the electron than the hydrogen. Okay, so that's why the hydrogen will lose electrons. So this will act as anode. Okay, and now the copper will act as a cathode. Since electrons are flowing from hydrogen, which is as a reference electrode, and we know the electrode potential of the hydrogen is taken as 0, whether it acts as an anode or a cathode. In both cases it is taken as 0. And we know the EMF of a cell is what? It is the oxidation potential of anode, right, plus reduction potential of cathode. Okay, and EMF of a cell, for example, is 0.34 volts. So therefore 0.34 volts, which is the EMF of a cell, will be equal to the oxidation potential of an anode. Anode here is the hydrogen, and therefore by convention we take its oxidation potential or reduction potential, its electrode potential, is a 0. That will be equal to then reduction potential of a cathode, right? So what you got here? We got the reduction potential of a cathode, which is the copper here, is equal to 0.34. Okay, so we can say that reduction potential of copper is how much? 0.34 volts. Okay, reduction potential of copper is 0.34 volt. What will be the oxidation potential then? Correct. What will be the oxidation potential of a copper? Again, I can change the reduction potential into this oxidation potential by simply changing the sign here, right? So if it is plus 0.34, I'll say it is minus 0.34 volts. Okay, so which means that copper has a higher reduction potential than oxidation potential. It has a high reduction potential and low oxidation potential, correct? That's why once you connect to the copper with the reference one, it will take electrons away from the hydrogen. Okay, so hydrogen will act as the anode. It will lose electrons, and the basic reaction which occurs at the hydrogen is actually H2. It will dissociate into H plus ions and electrons here. The electrons will start flowing here. They flow through the wire. Okay, and the copper will gain electrons. Okay, and it will undergo reduction here. Okay, so in both cases, what we find in the previous example, the zinc zinc gives electrons to the reference electrode, but in this one the copper takes electrons away from the hydrogen. That means if you compare the two electrodes here, the copper and the zinc, we say the copper has a high oxidation potential, the zinc has a high oxidation potential and the copper has a high reduction potential. By this way, we will be able to measure the electrode potential of the different electrodes, right? And then we can arrange the electrode potentials of the different electrodes in a particular sequence, right? And what we get is called as an electrochemical series, right? So electrochemical series is basically a series where electrode potentials, right? The electrode potentials of the different electrodes are arranged in according to their reduction potentials, correct? So suppose this is a series, this is an electrochemical series, and in this series we arrange the electrodes here according to their reduction potentials. We know the electrode potential is of two types. Okay, electrode potential, we say it is of two types: oxidation potential and reduction potential. But in electrochemical series, you can see here we are arranging the electrodes according to their reduction potentials, correct? So you can see here the hydrogen is in the middle with the electrode potential of 0.00, and you see here all these electrodes with a negative reduction potential. That means what? That means they are having actually the high oxidation potentials. Okay, if you see the lithium, it has a very, very low reduction potential, minus 3.05. What will be this oxidation potential? That will be plus 3.05. Okay, that means this particular electrode has a high oxidation potential, right? It has a high oxidation potential and a very, very low reduction potential. If you go down this series here, okay, if you go down the series here, what we find? We find that reduction potential increases. Okay, it becomes less and less negative, then becomes 0, and then again increases, correct? So down the series, what we find that reduction potential, okay, increases. So in this electrochemical series, we are arranging the electrodes according to their reduction potentials, right? So at the top is the one with the very less electrode reduction potential, as you go down the series, the reduction potential increases. If you see these electrodes, suppose you take the potassium, lithium, these are all the electrodes, sodium or calcium or whatever it is. We have taken one experiment with the zinc also. We find that the zinc loses electrons as soon as you connect it with the hydrogen. So why it is so? Because zinc has a high tendency to lose electron, right? So it has a higher oxidation potential. This is what? Minus 0.76. This is the reduction potential of the zinc, correct? So its oxidation potential will be plus 0.76, okay, 7628 to be more accurate. So that means if you take any electrode here which is above this electrochemical series, okay, if you take any of these electrodes and you connect them with the reference electrode, you'll find all these electrodes, as soon as you connect these electrodes with the reference electrode, they will act as cathode, anode. They will lose electrons, okay. That's why the zinc also loses electrons to the hydrogen, because all these electrodes, they have actually a higher oxidation potential than the hydrogen, okay. So that means in all the cases, whether you connect the zinc with the hydrogen, that will act as the anode, okay. If you connect the chromium also, it will act as the anode. The iron, all these electrodes, they will act as anode. They will lose electrons as soon as you connect them with the reference electrode with the hydrogen electrode. So this will, the hydrogen in that case will act as a cathode, okay. But if you do the other way, suppose if you connect these electrodes here, we have done an experiment with the copper, right? If you connect the copper electrode with the hydrogen electrode, we find the copper has a high reduction potential, okay. The reduction potential of hydrogen of the copper here is 0.337, or we have taken it as 0.34. The hydrogen has a 0 only, so that means copper has high tendency to gain the electron than the hydrogen. So that means the copper will act as a cathode once you connect it with the hydrogen. So hydrogen in that case will act as anode, okay. Hydrogen will act as anode, okay. Any electrode here down this series, you can just check the reduction potential is higher than the reference electrode. So that means these electrodes, they will act as what? All these electrodes, they will act as cathode, right? Whether you take any of the electrode here, the gold, the silver, the copper, any of these electrodes, you connect it with the hydrogen electrode. So hydrogen will act as anode in that case, and these will act as cathodes because they have high reduction potential, correct? So all these electrodes actually have been arranged according to their reduction potentials, right, in an electrochemical series. This electrochemical series has a lot of applications, right? We will discuss all those things in the next video. Hope you got the concept. Thanks for watching the video. Bye for now.